Imagine walking through a bustling café, your smart glasses capturing everything from your first-person perspective. A group of friends is chatting, laughter filling the air. One person turns toward you, smiles, and says, "Hey, I was just telling you about that movie." How does your device know who is speaking to you? This is the core challenge of talking to me, a pivotal task in egocentric video understanding. It's not just about detecting who's speaking, but who's speaking to you. And in real-world scenarios, things get messy fast. Overlapping voices, background noise, occluded faces, sudden camera movements, all of which can throw off even the most advanced AI systems. Today, we dive deep into EgoAdapt, a novel framework that redefines how we approach robustness in egocentric speaker detection, especially when key data is missing. Let's break it down. Most traditional models rely on either audio or visual cues alone. But real conversations are messy. Audio-only methods struggle with overlapping speech and background noise. If two people talk at once, the system can't tell who's addressing the camera wearer. Vision-only methods often misinterpret lip movements from yawning, eating, or emotional expressions as meaningful speech, leading to false positives. And when the camera moves, the speaker's face might be briefly occluded or even completely out of view. That's a critical failure point. Even state-of-the-art models like QuAVF and EgoT2, while impressive, still assume both modalities are present and well-aligned. But in real life, that's rarely true. So how do we build a system that doesn't just detect speaking, but detects addressing, reliably, even when parts of the signal are missing? Enter EgoAdapt. EgoAdapt isn't just another fusion model. It's a dynamic, adaptive framework built around three core innovations, designed to handle missing modalities in real time. First, visual speaker target recognition, seeing intent, not just speech. This is where EgoAdapt goes beyond basic speaker detection. Instead of just looking at if someone is speaking, VSTR analyzes who they're talking to using two key signals. Head orientation, nonverbal cue, is the speaker facing the camera wearer. That's a strong indicator of intent. Lip movement, verbal cue, are they mouthing words? But crucially, VSTR doesn't just detect motion, it interprets it in context. How does it work? The head pose is estimated using a 6D rotation representation, derived from a rep VGG backbone. This allows precise 3D orientation prediction, yaw, pitch, and roll, even under occlusion or varying scales. Meanwhile, the lip region is processed via a vision transformer, using patch-based encoding with positional embeddings. The CLS token captures global semantic features, giving a high-level representation of lip dynamics. Together, VSTR learns to distinguish between someone talking and someone talking to me, even in crowded, multi-speaker scenes. And here's the key insight. Head orientation is a powerful nonverbal signal. When someone turns toward you, it's often a deliberate act of engagement, far more reliable than lip motion alone. Now, what happens when the cafe is loud? Or there's music playing? This is where the PSA encoder shines. Traditional audio encoders struggle when noise is mixed with speech. But PSA takes a different approach. It processes both clean and noisy audio simultaneously, using shared weights. Here's the trick. For each audio segment, the model receives two inputs, clean speech and noise-mixed speech. Both are converted into MEL spectrograms. They're fed into the same whisper-small encoder, which has been pre-trained on 680,000 plus hours of diverse speech data. The loss function, mean squared error between the embeddings of clean and noisy inputs. This forces the model to learn noise-invariant features, focusing on the core structure of speech while ignoring background interference. In effect, the PSA encoder learns to generalize across noise levels. It doesn't just filter noise, it learns to understand speech despite noise. And the result? A model that doesn't just survive in noisy environments, it thrives in them. The final piece. Knowing when to trust vision and when to trust audio. VMMA is a real-time modality-aware mechanism that assesses, frame by frame, whether visual data is available. It uses a dual-level prompt system. Fine-grained, tracks frame-by-frame presence of head crops. If a face is missing, the prompt activates. Coarse-grained, computes the ratio of missing frames over a segment. If more than a threshold, say 20%, the system shifts focus to audio. But here's the innovation. The threshold is adaptive. Instead of a fixed value, VMMA uses beta t equals mean delta c plus k std delta c. So the model learns optimal sensitivity based on the data, whether it's a quiet room or a chaotic party. This allows EgoAdapt to dynamically adjust its reliance on visual versus audio cues, switching seamlessly when the camera pans away or a speaker turns their back. No more rigid fusion. No more brittle assumptions. Just adaptive intelligence. Now let's see how these components interact. The visual audio fusion module is where the magic happens. It uses a multi-stage cross-attention architecture. Head-lip cross-attention. Head pose features query lip motion features, capturing how head movement aligns with speech. Lip audio cross-attention. Lip motion queries audio, reinforcing the link between mouth shape and sound. Audio head cross-attention. Audio queries head pose, checking if speech rhythms match head orientation. These three outputs are summed into a unified representation, ZHLA. Then the VMMA prompt is concatenated, injecting real-time awareness of missing data. Finally, this combined signal passes through a self-attention block, refining the representation before the final TTM prediction. Talking to me or not talking to me. This isn't just fusion. It's context-aware, temporally sensitive, and modality-aware reasoning. On the Ego 4D TTM benchmark, EgoAdapt achieves 62.01% accuracy, 67.39% MAP. That's a 4.96% improvement in accuracy and 1.56% gain in MAP over the previous state-of-the-art, QuAVF. But the real story is in the ablation studies. When you remove any one component, no VSTR, drop in MAP by, especially in multi-speaker scenes. No PSA. Performance plummets under low SNR, losing 0.09 in MAP at dB. No VMMA. Accuracy drops by nearly 4% because the model can't adapt to missing data. But with all three, 81.14% accuracy, 84.83% MAP, a clear victory. And visually, in multi-speaker environments, EgoAdapt correctly identifies the speaker facing the camera, while others mislabel listeners as speakers. In noisy settings, while others fail, EgoAdapt maintains accurate detection, even when speech is partially masked. And when the camera moves, while others lose track, EgoAdapt shifts to audio, using context, timing, and voice direction to keep predicting correctly. EgoAdapt isn't just a better model, it's a paradigm shift in multimodal AI. It moves beyond the idea of fusion, where you combine signals like ingredients in a recipe. Instead, it embraces adaptation, where the system understands when to rely on one modality over another, based on real-time conditions. It's more robust, more intelligent, and more human-like in its reasoning. And that's critical for real-world applications. Assistive technologies for the visually or hearing impaired. Smart glasses that understand social cues in real time. Human-robot interaction, where robots know who to respond to. AI companions that don't just hear you, they see you. We're moving beyond static, assumption-heavy models. The future is adaptive, resilient, and context-aware. EgoAdapt shows that by combining spatial reasoning, head pose, temporal robustness, PSA, and dynamic awareness, VMMA, we can build systems that don't just survive real-world chaos, they thrive in it. So the next time your smart glasses say, that person is talking to you, know that it's not magic. It's EgoAdapt. And it's just the beginning. If you found this deep dive valuable, hit like, subscribe, and let me know in the comments. What's the next frontier in multimodal AI?